Okay, our unit's on EMR. In my mind, I always think of light when I think of EMR, just because that's the form of EMR that I'm most familiar with. Hopefully you guys remember talking about this at some point in your lives otherwise, but electromagnetic radiation is really a spectrum of different wavelengths. Okay. The longest wavelengths are radio waves, all the way down to like microwaves, ultraviolet, X-rays, gamma rays. Does that make sense? You guys, have we talked about this before? When I think of EMR though, I just think of light. Because, I don't know, I think it's I'm most familiar with light. Does that make sense? So, but really all of these things behave fairly similarly. First thing I need to remind you of is the speed of light. We've actually used this number before, 3 times 10 to the 8 meters per second. Okay. The most common formula we used it in was, where was it? The velocity is equal to a frequency times a wavelength. Is that the formula? Write that one down right. And the velocity we often would have used was 3 times 10 to the 8. We were using that for waves in general though. Do you guys remember what we used when it was like a sound wave? Remember what the speed of sound approximately was? 300. It's about 330, 340. Depends on temperature and altitude and some of those other factors. But this unit here, when we talk about waves, we're going to specifically talk about the EMR waves. So, before I move on, do you guys remember these terms, frequency and wavelength? Frequency is basically like how fast they occur. Frequency is measured in hertz. You guys remember the formula frequency is equal to 1 over your period? Or period is equal to 1 over your frequency? Basically, it's the amount of time it takes to make, like, say, one rotation or one up and down kind of thing. Right? Actually, frequency is how many times that happens in a second. Period is how long it takes. Does that make sense? And then wavelength is, for you guys in my Math 30 class, this right here is defined as a wavelength, like between sine, like as a sine curve, from like top to top, or from, say, bottom to bottom. That's a wavelength. You guys in 20, we'll talk about this next year, obviously. Does that make sense? Okay. Okay, a couple other notes here then. Here's that formula again, V equals F times lambda. EMR will always travel at the same velocity. And later on in this lesson, I'm actually going to show you guys some experiments where physicists discovered how fast light truly travels. Like, we'll show you the experiments they did. Here's something new that I'm only just going to briefly explain, mostly because I don't even fully understand it myself, to be honest. We've discovered, though, that EMR really involves accelerating charges. That's the reason why we have electromagnetic radiation. Light, radio waves, whatever sort of EMR we're talking about, is based on accelerating charges, based on perpendicular electric and magnetic fields. Hopefully I'll do a good job of explaining this over the next little while, because it's a pretty deep concept. The idea is whenever you have these waves, they're actually not just in one direction. They actually propagate in both the X, Y, and Z directions. You know what I mean when I say like X, Y, and Z? So like up, over, but also like out of the page. So here's the best diagram I could find to describe this. What really happens in an EMR is there's a magnetic field that might be coming, say, out of the page, and it keeps going back and forth, just like a sine wave. And then we just learned in our last unit, well, what happens when you have magnetic fields and electric fields? Aren't they kind of similar to each other? Like, moving electric charges makes a magnetic field. Well, then a moving magnetic field actually makes an electric field. And it produces this cycle going on and on and on, where magnetic makes electric, which makes magnetic, which makes electric, that makes sense. And so in the Z direction is a magnetic field. In this direction here, the Y direction, would be the electric field. And in this direction is actually the direction of travel. So we've discovered these EMR waves are actually like way more complicated than just a straight up and down sine wave. There's actually multiple components to them. I'm not sure whether you'll get tested on this or not, but I want to be thorough. I've said this a lot before. Like, I'm going to try to cover I'm going to cover all the bases. So one of the most important scientists that you might get asked about is James Maxwell. Have we talked about him before? Okay. So I'm just I'm going to do what I hate doing, but I'm going to more or less read off my slides here. You guys remember Oersted from the previous unit? Oersted was basically the guy that figured out that if you have a wire and electrons are running through the wire, if you put a compass over here, you had a question on your test about this, where there were like 4 compasses in different locations. He figured out your first right-hand rule or left-hand rule, figuring out where the deflection would be going around in a circle. You guys remember that? Right. So he figured out that current will make a magnetic field. Faraday, he's the guy who kind of discovered the opposite of that. He figured out that if you have a wire moving compared to a magnet, it'll actually induce electricity. So we did this in our lab, actually. That's where I gave you like the solenoid and the magnet, and you guys are taking the magnet and the solenoid, moving them towards each other, and then it caused the little ammeter to deflect, thereby making current. You recall that? Well, Maxwell took these two ideas and put them together. Said, look, if current, which is more or less like electric, can make magnetic, and if a magnetic field can make electric, it's almost like there's a cycle here. You guys get what I'm going for here? The idea of electric makes magnetic, which then remakes electric, which then remakes magnetic. Here's where I said this to Justin a little bit earlier. I understand the what. I don't know the why, to be honest. So I can describe to you what's happening. I get the idea that electric makes magnetic, but for the life of me, I don't actually know like the why this is happening so much. Okay, long story short, Maxwell had a famous paper back in 1865 where this is basically what I just said. A changing electric field makes a magnetic field, which just makes an electric field. And he basically figured this is EMR. This is light or X-rays or gamma rays or whatever sort of EMR we're talking about. Is these changing fields. Okay. So he basically had like 5 or 6 different ideas, put them all together in a paper. So here's the main ones. First one is anytime you have a charge accelerating, it produces EMR. If a charge is moving, what does a moving charge produce? A magnetic field. But what happens if you then have a moving magnetic field? It produces M, which then propagates the magnetic and electric. Does that make sense? That's what he figured was happening. So really, when you see light, the theory is that that's actually the result of some sort of moving charge. Weird, right? Okay. Next one here. The frequency that a charge moves with will match the frequency of the EMR produced. Okay. I mean, all charges are going to be moving, obviously, if we're talking about this, right? Eventually, we're going to talk about Hertz's experiment where he had charges going back and forth. And the frequency at which they moved back and forth, he figured must be the frequency of like the wave produced. Like for example, if they move back and forth this frequency, maybe that's a radio wave. But if they move back and forth this frequency, now that's an X-ray. Does that make sense? Third postulate, EMR travels the speed of light. I mean, probably one of the biggest reasons why is, well, light is a form of EMR. These electronic and magnetic fields are perpendicular to each other. So like that's the diagram I kind of have here. And they're also perpendicular to the actual direction of travel. EMR behaves just like any other wave. So that means you can refract them. Do you guys know what refraction means?
Bend.
Yes, perfect, bend, yeah. We've got a whole lesson on this next week. But do you guys ever see like light where's a good example? You put like say a pencil in a cup of water, and then the light actually bends it to look more like this in the water. You guys ever seen that before? Or another good example is like if you're trying to spear fish, and you want to try to spear the fish, and like you can see where your spear is in the water, but like really the angle is actually off compared to things because of the way that light bends. Does that make sense? So that's refraction. We'll talk about interference later too. I also missed one. There's also reflection. Reflection. That's actually tomorrow's lesson, talking about how waves can reflect off of things. And then the last one, basically this formula is applicable for EMR, which we've kind of already been using. Maxwell is famous for his 4 equations. I don't know these. I don't expect you to know these. I thought I'd show them to you. I have no idea how they work, to be honest. I didn't take physics to this level. So if you eventually do learn how the Maxwell equations work, then come explain it to me. So I thought I'd show it to you though. So these are the famous Maxwell equations. Anyways. They're not on your formula sheet. We're not talking about them. But Maxwell's famous for them. Okay, another guy I want to talk about in history, hertz. We've talked about hertz before because a hertz is like the unit for frequency. So obviously we named the unit frequency hertz after this guy. I want to try to describe a famous experiment he did, and then I've got a video that will hopefully help to explain it even better. So basically what he did is he tried to create the first more or less radio waves. He didn't know this probably at the time, but he tried to create a transmitter that would emit waves and then something that would actually pick them up on the other side, like a, I guess, transmitter and receiver. You always have to have like two halves, right? So here's his experiment. He more or less has like a battery high voltage pack right here, and he's got a spark being produced between a gap here. And so the idea is using, I believe, alternating current, there's going to be a spark going back between this little gap here. Kind of like a spark plug, I guess, right? And as this charge accelerates back and forth, a moving charge will then create a magnetic field, which will create an electric field, which will create a magnetic field. Does that make sense? And so the frequency of this wave then is being sent out in all directions. While over here, he created a receiver, which would hopefully then pick up that wave, yes. It's actually the same concept that we have for, like, say, radio signals, where you have a tower that emits out the signal, and somewhere else you might have to have some sort of equipment to then pick up that signal. So let me show this video here. Oh, sorry.
Can we do that?
I don't have the apparatus. Sorry. I hope this kind of makes sense, though. Let's try this. Okay.
Around 1880, the brilliant scientist James Clerk Maxwell developed the mathematical theory of electromagnetism. His theory predicts that electromagnetic waves propagate through space at the speed of light. Many other scientists of the time were trying to prove experimentally the existence of these waves. In 1887, Heinrich Hertz, a German physicist, designed a series of brilliant experiments to demonstrate Maxwell's hypothesis. Heinrich's equipment was simple: a spark generator coupled to an antenna and a metallic ring set at some distance apart. Heinrich proposed that the electromagnetic waves generated at the antenna will travel through space, and, if Maxwell's theory was correct, they would induce a current in the ring, and a spark will appear in the ring gap. In this video, we make a simplified version of this famous experiment. This project requires a high voltage pulse in order to work, and we will obtain that pulse with a lighter like this. Here we have one that we have modified for our purposes.
Alyssa Fisher, go to the library. Alyssa Fisher to the library, please.
Here it is. This is a Here it is. This is a piezoelectric element that produces a pulse of several thousand volts. There are these two wires that come from the piezoelectric, and we have connected these two wires in order to
create a spark, basically,
be able to get the pulse. Here we can see the spark jumping when we pull the
Does
trigger.
that make sense? So really the charges are jumping from one side to the other, right?
This is our setup to replicate Hertz's experiment. We have the spark generator connected to these two wires, and the electromagnetic waves will travel through the receiving antenna. Here we have a neon lamp connected to the antenna, and when the spark is produced here,
So I mean, really, you've
the
got
neon
a
lamp will
transmitter,
glow.
and then the other side is a receiver, right? No, there's no wires
Okay, I
actually
will
connecting
pull the
this.
trigger to generate the spark,
But the waves are.
and we can see the lamp glowing along with the spark.
Just want to pause there for a second. Think about the implications of this and how this has affected our modern society. I mean, your cell phone. Right? Anything that's wireless, right? That's really what this essentially is doing. Is right. It's sending an electromagnetic wave, so that you don't actually have to have things plugged in anymore. And I mean, the more and more we're getting better and better at the technology here, the more we're using these sorts of wavelengths. Does that make sense? Right. So I mean, he was basically able to cause a light bulb over there to light up, no wires, just based on what I mean. This guy's clicking a lighter. Does that make sense? And the spark that's getting caused from the lighter is causing an electric charge to move, an accelerating electric charge. Then moving charges makes a magnetic field, which makes sense, right? And that gets picked up over here, causing the light bulb to turn on. I don't know. To me, that's like, wow, that's crazy cool. So I'll just finish the rest of the video.
We will now try a more powerful arrangement. We are using now high voltage power supply. You can build this power supply following the link to the video that is now on the screen. This power supply outputs several thousand volts. The output of the power supply is connected to this capacitor. The capacitor stores the energy, and the spark will be more powerful in our transmitting antenna.
That is so cool.
Yeah. Again, I don't think I have the stuff for this. Or the know-how. It's pretty cool, eh?
So cool. Now we'll make it more powerful.
Yeah.
Like ball breaks. That is so cool.
Does that make sense?
I do.
Again, this is where I said to Justin earlier, this is why I love science, because, man, we're still figuring this stuff out. I mean, really, when did cell phones start becoming more popular? I mean, 10 years ago, maybe? Like, I graduated high school in 2002, and like maybe 5% of kids would have had cell phones at that point. Right? Now it's 2015, so 13 years later. Like, who doesn't have a cell phone now, right? So I mean, think about how much better companies have gotten at figuring out how to use like wireless technology, right? We use wireless stuff for everything. Our cordless phones, the baby monitor I used last night to keep track of Kinsey and Cami in their room, right? Like all of this stuff. The television remotes we use, they run on IR, infrared. Does that make sense? It used to be that you had to like literally get up off your butt off the couch and go to the TV and turn the channel, right? Now you just have a remote and do it. Sure. Alright. Okay, I got another video we'll show you. There's a lot of videos today. So, Hertz basically helped us figure out the ideas behind, you know, transmitters and receivers of EMR, figuring out more or less what it is. Trying to figure out what it is. Scientists have now been trying to figure out for the longest time what the speed of electromagnetic radiation is. When I started the lesson by saying that I always think of light, it's probably because most of these guys were also thinking of light when they were doing their experimentation, because they didn't really work with X-rays back in the 1400s. You know what I mean? Now we work with X-rays more often. But when we were talking about trying to measure EMR, they were more or less measuring light. So I want to show you guys a video basically about how scientists in the past tried to measure how fast light traveled.
Let there be light. Assuming you are sitting in a normal-sized classroom, it took that light about 10 nanoseconds to reach you. In turn, for you to have known that the light has reached you, it took about 200 milliseconds. Congratulations, you are about 20 million times slower. As you can see, the speed of light is so fast that it precedes our immediate perception. So how do people measure it? More specifically, how did people before the 20th century try to measure it? Did they get close to the real answer? During Galileo's time, many believed that the speed of light was infinite. In fact, they had no reason not to believe that. Galileo, being Galileo, disagreed. He tried an experiment in which he and another person each took a shuttered lantern and walked a mile apart. The rule was that as soon as one of them flashed his lantern, the other would flash back, and Galileo would simply divide the distance by the time. He found that the speed of light was at least 10 times greater than the speed of sound, or 3.4 kilometers per second. Little did they know, they did more to measure the reaction time and the speed of their arms. Galileo had less success in measuring the speed of light than he had in avoiding trouble with the Catholic Church. During the 1670s, inspired by Galileo's discovery of Jupiter's moons and his belief in the finite speed of light, Danish astronomer Ole Romer made another attempt at measuring the speed of light. Initially, Romer was trying to predict the orbital times of Jupiter's moon Io. To his frustration, however, he discovered that Io was not orbiting strictly on schedule. Romer simply did not accept the possibility that Zeus might have been keeping Io late from the telescopes. He noticed that Io was ahead schedule when the Earth was closer to Jupiter and behind schedule when Earth was farther away from Jupiter. Romer deduced that the irregularities in Io's orbit must have been due to this finite speed of light. Based on careful observations, his data implied that the speed of light was about 300,000 kilometers per second.
Which is basically 3 times 10 to the 8 meters per second. So
In France, 1849, Louis Fizeau produced another measurement for the speed of light. Fizeau shone a beam of light through a rapidly rotating tooth wheel into a mirror 5 miles away. The mirror reflected the same beam of light back through the rotating wheel. By varying the wheel's rotational speed, Fizeau could see when exactly the light does not have enough time to be reflected back through the same gap in the wheel. His speed of light was about 313,300 kilometers per
A
second.
little bit over, but pretty close.
In France, 1862, Leon Foucault modified Fizeau's experiment and made a more accurate measurement of 299,796 kilometers per second. The actual value of the speed of light is 299,792.458
Which we round to 3 times
kilometers
10
per
to the 8.
second. There are a number of different ways to measure speed of light now. One of them is remarkably similar to Galileo's method. Astronauts put a mirror on the moon, and when a laser on Earth shoots the mirror, our atomic clocks combine very accurate times for the laser to travel there and back, which is about 2.5 seconds. So remember, next time you Google the speed of light, give a second of silent tribute to the people that worked so hard to make our life just a bit easier.
Okay, I'm going to actually skip ahead and show you another video here. This one here. You guys ever watch Big Bang Theory?
Yeah.
Ever seen this one? Basically, they're trying to do the experiment the guy in the previous video just talked about, where, well, I'll just play it.
This is my friend Zach.
Hey, hello. Whoa, is that the laser? Fishing.
It's not very loud. Sorry, guys.
In 1917, when Albert Einstein established the theoretic foundation for the laser and his papers are quantum theory of Stralum, his fondest hope was that the resultant device be bitchin'. Mission accomplished.
Let me explain what we're doing here. In 1969, the astronauts on Apollo 11 positioned reflectors on the surface of the moon, and we're going to shoot a laser off one of them and let the light bounce back into this photomultiplier.
Oh, very cool.
One question. How can you be sure it won't blow up?
The laser?
The moon. See, now this is a man for pennies.
That's a great question, Zach.
No, it's not.
Sheldon, play nice.
Well, it's not a great question. How could somebody possibly think we're going to blow up the moon? That's a great question.
Don't worry about the moon. We set our laser to stun.
Smart.
Now, we'll be able to see the beam when it leaves, but it won't be strong enough when it comes back to be seen by the naked eye.
Yeah, you could.
Funny. That device there will measure the photons that return and we'll see it on this computer. I'll have to get them some glasses.
Cool, it's going to be in 3D. Preparing to fire laser at the moon. Make it so. There it is. There's the spike.
2.5 seconds for the light to return. That's the moon. We hit the moon.
experiment? Or light on the string?
Yeah, but think about what this represents. The fact that we can do this is the only way of definitively proving that there are man-made objects on the moon. Put there by a member of a species only 60 years before I just invented the airplane.
What species is that? I was wrong. Penny can do better.
Okay, guys, thank you. It's been fun.
Yeah, thanks.
Okay, so that's more or less the experiment the one video was describing there, where they shoot a laser at the moon. I mean, the moon's so far away, it actually takes a little bit of time for light to get there and back. And so, I mean, at the distance the moon is from us and at the speed of light, it's about 2.5 seconds. So, does that make sense? Okay, there's one more experiment that I kind of glossed over here. This one is by Michelson. And I hope I can explain this one well, because it's tricky to understand. You know, I even struggle with it sometimes. Here's their idea. They wanted to shoot light at an octagonal mirror, and then hits a curved mirror. It would come back again. I guess it's coming from this side, I guess, so let me try it again. Shoot the light at an octagonal mirror. The light would then bounce down off of this curved mirror, bounce back up, hit the octagonal mirror again, and then go through here. And they set this so that it was like 35 kilometers away. So a fairly long distance for light to travel, obviously, right? And so the idea here is that they're then going to cause this mirror to spin. Okay? And so as the mirror spins, if it's set up correctly, sometimes the light will hit this, bounce there, go up, and you'll actually be able to see it. But if the mirror is kind of in the wrong location, the light would not bounce in a way that you could measure it over here again. Does that make sense? And so they basically had to figure out, well, what frequency does this thing need to spin at in order to actually observe the light? And I basically copied this out of your textbook. He discovered that when the mirror traveled at 3,200 RPMs, he could observe light in the telescope. So long as this thing was traveling a certain speed, he was able to visualize the light. Because, I mean, as it rotates, let's see if I can describe this here. As it rotates, now this one will now be sitting here, and then this one will now be sitting here. So by the time the light goes from here down to here and back up again, hopefully this thing will have turned like an eighth of a turn, so the light can keep going. Does that make sense? But if the thing has actually turned a little bit too far, or a little bit not far enough at that point, then you won't measure the light. So long story short, he figures out that he needs about 533 hertz. So they did some calculations, I have them below. If frequency and period are related by this formula, he was able to figure out the amount of time that it would have taken. So like a frequency would be 1 divided by your hertz, so he had a time value. Does that make sense? And then for his time value, he figured, well, really though, it needs to be an eighth of that, because each of these things is like equal in terms of size, so he divided by 8. So that's really what's happening here. So he has a new time value. And then finally, he took his distance and divided by that time. And so in doing distance divided by time, this right here should hopefully be about your 35 kilometers? Why is that 35 kilometers? Doubled it. That's why. There and back, yeah. That would make sense. Because this is 35 kilometers here. So it's like 35K this way, 35K this way. Does that make sense? So that's your 75K, or 70K basically. Take that divided by your time. Here's how we calculated the speed of light, more or less. Does that make sense? So I don't really know how you'd ever get tested on this, right? But I just want you guys to know basically the idea behind some of these experiments. They were more or less figuring out distance divided by time, and that's the speed of light. So we round this thing to 3 times 10 to the 8 meters per second. So anyways, in terms of this page right here, I just wrote down, at some point, can you guys just read through chapter 13.2? Again, I'm not exactly sure how much assessment there will ever be on any of these famous scientists, but read them anyways, just so you're prepared. Does that work? Okay. Okay, one last slide, then we're going to take a break, because I've even got another movie to show you. Today's kind of a long lesson. So, the last thing I have here before we break then is there's 2 main ways that we detect EMR. One of them is kind of the the first experiment, the Hertz experiment, we can measure it directly if it's unimpeded. Right? That's what Hertz did, is he set up his receiver and his transmitter, right? And it directly, caused the electromagnetic radiation to go from here to here, and he was able to measure that. That makes sense? So that's one way of measuring it. The second way is kind of that Big Bang Theory experiment, where they reflected it, right? So you send the EMR from here to the moon and back, and through changing it, then we can measure how fast it was going. Does that make sense? Okay, let's pause there. Go take a 5-minute break because I've got another, this next video is about half an hour long. Yeah, so. Yeah, I'm pretty much talking at you all day today, so sorry. Start this again. So what I want to talk about now, basically, and all of this is on slides, and I hate reading off the slides, because I think you guys can just read it yourself, and it's all in your textbook. But I need you guys to know about most of the different types of EMR spectrum. So the longest spectrum are either low frequency AC or your radio waves. Those are the longest waves we have. Okay. I didn't know this actually, but when you guys tune into a radio station like 960 AM, the 960 actually refers to how many kilohertz the frequency is at. I didn't know that until this. Okay, that's different. That's on FM. I don't know how that works. But on AM station, if you tune into 1030 AM, that's actually the frequency in kilohertz. So that would be 1030000 hertz. That makes sense? That's actually the frequency at which I guess totally makes sense, doesn't it? So I don't know how FM works. I gotta look into that. I actually don't know that either.
AM morning.
Yeah, none of the good radio stations are on AM, so. Alright. We're working downwards in terms of length. Then microwaves are after radio waves, which seems kind of odd because micro means small, but these are actually not very small waves at all. They're actually second largest waves still. They're just smaller than radio waves. Does that make sense? So microwaves are next, which we actually use to cook our food. And something else I didn't know, but they actually match the natural frequency of water. That's the purpose behind a microwave, because most of the food we have has water in it. Therefore, when the microwaves heat up your water molecules and make the water molecules move faster, it's heating up the water in your food, which is in most of your food. That makes sense? So I didn't know that was actually purposefully what it was set for, to match water. You guys remember the term resonance? The idea of a kid on a swing, if you push him at the right moment, it'll cause him to go faster and faster and faster. Right? Everything has a natural frequency. I grabbed those tuning forks last year. Right? You hit the tuning fork and it has a specific frequency. So, anyways, microwaves are next. Then there's infrared, which is right before visible light. We use IR for various things, like I mentioned remote controls, we use them for that. After infrared is our visible light spectrum, which is kind of right in the middle, which goes from red down to violet. You guys have probably seen this acronym before for red, orange, yellow, green, blue, indigo, violet, back in kindergarten. So, X-rays are after visible light. Oh wait, there's one missing here. You should have UV light after visible light. I don't know why I missed that one, but UV light should be in between there. Where's a picture of a spectrum? We have one on the first page here. Yeah. After visible light should be ultraviolet light. Sorry, I didn't put anything on ultraviolet.
Where? After what?
After visible light is ultraviolet light. You guys have heard of UV rays before, right? Mostly about sunburns and stuff like that. You want to avoid that sort of. X-rays are after UV. When I think of X-rays, I think of medical stuff, right? So, the point of X-rays is that these waves can actually pass through your body now. So the waves will actually pass through flesh, but they won't pass through bone. So that's why you can basically get those X-rays, because it'll actually scope the inside of your body out. Gamma rays are next. We use these to try to kill off cancer. So they use gamma rays in chemo. They're also the radiation after nuclear stuff. Cosmic rays are the shortest into their wavelengths and highest frequency. And we actually know very little about these. They are dangerous, but they pass through all matter. Like, they are so small, these waves, that they will actually phase through your body, completely unnoticeable. Does that make sense? So, okay. Rather than me talking, though, I found a YouTube video that's gonna go in pretty good depth about all the different electromagnetic spectrum stuff. So I thought we'd watch this for a while. This might add more than what I could just tell you.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum. All electromagnetic radiation is light. Visible light is the only part of the spectrum you can see. For all your life, your eyes have relied on this one narrow band of EM radiation to gather information about your world. Though our sun's visible light appears white, it is really the combined light of the individual rainbow colors with wavelengths ranging from violet at 380 nanometers to red at 700 nanometers. Before Isaac Newton's famed experiment in 1665, people thought that a prism somehow colored the sun's white light as it bent and spread a sunbeam. Newton disproved this idea by using two prisms. To show that white light is made up of the bands of colored light, Newton used a second prism to show that the bands of colored light combine to make white light again. Visible light contains important scientific clues that reveal hidden properties of objects throughout the universe. Minute gaps in energy at specific visible wavelengths can identify the physical condition and composition of stellar and interstellar matter. Human eyes aren't nearly sensitive enough to detect these faint peaks, but scientific instruments can. Scientists can learn the composition of an atmosphere by considering how atmospheric particles scatter visible light. Earth's atmosphere, for example, generally looks blue because it contains particles of nitrogen and oxygen, which are just the right size to scatter energy with the wavelength of blue light. When the sun is low in the sky, however, light travels through more of the atmosphere and more blue light is scattered out of the beam of sunlight before it reaches your eyes. Only the longer red and yellow wavelengths are able to pass through, often creating breathtaking sunsets. When scientists look at the sky, they don't just see blue, they see clues about the chemical composition of our atmosphere. However, visible light reveals more than just composition. As objects grow hotter, they radiate energy with a shorter wavelength, changing color before our eyes. Watch a flame shift from yellow to blue as it is adjusted to burn hotter. In the same way, the color of stellar objects tells scientists much about their temperature. Our sun produces more yellow light than any other color because of its surface temperature. If the sun's surface were cooler, say 3,000 degrees Celsius, it would look reddish, like the stars Antares and Betelgeuse. If the sun were hotter, say 12,000 degrees Celsius, it would look blue, like the star Rigel. Like all parts of the electromagnetic spectrum, visible light data can also help scientists study changes on Earth, such as assessing damage from a volcanic eruption. This NASA EO1 image combines both visible and infrared data to distinguish between snow and volcanic ash and to see vegetation more clearly. Since 1972, images from NASA's Landsat satellite have combined visible and infrared data to allow scientists to study changes in cities, neighborhoods, forests, and farms over time. Visible light images taken by NASA's Mars landers have shown us what it would look like to stand on another planet. They have expanded our minds, our imagination, and our understanding. NASA instruments can do more than passively sense radiation. They can also actively send out electromagnetic waves to map topography. The Mars Orbiting Laser Altimeter sends a laser pulse to the surface of the planet, and sensors measure the amount of time it takes for this laser signal to return. The elapsed time allows the calculation of the distance from the satellite to the surface. As the spacecraft flies above hills, valleys, craters, and other surface features, the return time varies and provides a topographic map of the planet's surface. Back in Earth orbit, NASA's ICESat mission uses the same technique to collect data about the elevation of the polar ice sheets to help monitor changes in the amount of water stored as ice on our planet. Laser altimeters can also make unique measurements of the heights of clouds, the top of the vegetation canopy of forests, and can see the distribution of aerosols from sources such as dust storms and forest fires. Finally, visible light helps us to explore the far reaches of the universe that humans could not hope to reach physically. Using visible light, the Hubble Space Telescope has created countless images that spark our imagination, inflame our curiosity, and increase our understanding of the universe. Guglielmo Marconi's first radio transmissions in 1894 have spread into space for over 100 years at the speed of light. They passed Sirius in 1903, Vega in 1919, and Regulus in 1971. That signal has already passed over 1,000 stars. Anyone orbiting one of those stars with a really good receiver could detect Marconi's signal and know that we are here. Radio waves are the longest and contain the least energy of any electromagnetic wave. While visible light is measured in minute fractions of an inch, radio waves vary from about 19 centimeters, about the length of a water bottle, to waves the length of cars, ships, mountains, all the way up to monstrous waves longer than the diameter of our planet. Heinrich Hertz discovered radio waves in 1888. The first commercial radio station went on the air in Pittsburgh, Pennsylvania on November 2nd, 1920. Then, in 1932, a major discovery by Carl Jansky at Bell Labs revealed the stars and other objects in space radiated radio waves. Radio astronomy was born. However, scientists need giant antennas to detect weak, long wavelength radio waves from space. The enormous Arecibo radio dish antenna measures 305 meters in diameter, over 3 football fields. Scientists can link the signals from an array of separate radio antennas to focus on tiny slices of distant space. Such arrays act as a single immense collector. This giant New Mexico array uses 27 parabolic dish antennas shaped into a giant Y, with each arm capable of stretching for 13 miles. Scientists have even spread these linked antennas across the globe. One of the largest stretches from Hawaii to the Virgin Islands and acts like such a powerful telephoto lens that a baseball sitting on the moon would fill its entire field of view. Many of the greatest astronomical discoveries have been made using radio waves. Pulsars, the existence of giant clouds of superheated plasma, which are among the largest objects in the universe, and even quasars, such as this one over 10 billion light-years away, were all discovered using radio waves. Radio waves also provide more local information. Astronomical objects that have a magnetic field usually produce radio waves, such as our sun. Thus, NASA's stereo satellite is able to monitor bursts of radio waves from the sun's corona. Wave sensors on the WIND spacecraft record the radio waves emitted by a planet's ionosphere, such as the bursts from Jupiter, whose wavelength measures about 15 meters. Radio waves fill the space around us to bring entertainment, communications, and key scientific information. We can't hear these radio waves. When you tune your radio to your favorite station, the radio receives these electromagnetic radio waves and then vibrates a speaker to create the sound waves we hear. We may not be able to tap our toes to the cosmic radio transmissions, but we certainly discovered much about our universe's grand cosmic dance by listening to them. When you use a remote control to change channels on your TV, your remote is using light waves. But this light is beyond the visible spectrum of light you can see. Back in 1800, William Herschel conducted an experiment measuring the temperature changes between the colors of the spectrum, plus one measurement beyond visible red. When that thermometer registered a temperature warmer than all the other colors, Herschel had discovered another region of the electromagnetic spectrum, infrared light. This region consists of short wavelengths around 760 nanometers to longer wavelengths about 1 million nanometers, or about 1,000 micrometers in length. We can sense some of this infrared energy as heat. Some objects are so hot they also emit visible light, such as a fire. Other objects, such as humans, are not as hot and only emit infrared waves. We cannot see these infrared waves with our eyes alone. However, instruments that can sense infrared energy, such as night vision goggles or infrared cameras, allow us to see these infrared waves from warm objects like humans and animals. Infrared energy can also reveal objects in the universe that cannot be seen with optical telescopes. Infrared waves have longer wavelengths than visible light and can pass through dense regions of gas and dust with lower scattering and absorption. When you look up at the constellation Orion, you see only the visible light. But NASA's Spitzer telescope was able to detect nearly 2,300 planet-forming disks in the Orion Nebula by sensing the infrared glow of their warm dust. Each disk has the potential to form planets and its own solar system. Incoming ultraviolet, visible, and a limited portion of infrared energy, together sometimes called shortwave radiation, from the sun drives our Earth system. Some of this radiation is reflected off of clouds, and some is absorbed in the atmosphere. Larger aerosol particles in the atmosphere interact with and absorb some of the radiation, causing the atmosphere to warm. The heat generated by this absorption is emitted as long-wave infrared radiation, some of which radiates out to space. The solar radiation that does pass through Earth's atmosphere is either reflected off snow, ice, or other surfaces, or is absorbed by the Earth's surface. This absorption of radiation warms the Earth's surface, and this heat is emitted as long-wave radiation into the atmosphere, which allows only a small amount to radiate out to space. Greenhouse gases in the atmosphere, such as water vapor and carbon dioxide, absorb most of this emitted long-wave infrared radiation, and this absorption heats the lower atmosphere. In turn, the warmed atmosphere emits long-wave radiation, some of which radiates towards the Earth's surface, keeping our planet warm and generally comfortable. The energy entering, energy reflected, energy absorbed, and energy emitted by the Earth system constitutes the components of the Earth radiation budget. A budget that's out of balance can cause the temperature of the atmosphere to increase and eventually affect our climate. For scientists to understand climate, they must also determine what drives the changes within the Earth's radiation budget. The Ceres instrument aboard NASA's Aqua and Terra satellites can measure the reflected shortwave and emitted long-wave radiation into space accurately enough for scientists to determine the Earth's total radiation budget. Other NASA instruments monitor the changes in other aspects of the Earth's climate system, such as clouds, aerosol particles, or surface reflectivity, and scientists are examining their many interactions with the energy budget. A portion of solar radiation from the sun that is just beyond the visible spectrum is referred to as near-infrared. Scientists can study how this radiation reflects off the Earth's surface to understand changes in land cover, such as growth of cities or changes in vegetation. Our eyes perceive a leaf as green because wavelengths in the green region of the visible light spectrum are reflected, while other visible wavelengths are absorbed. Yet the chlorophyll and the cell structure of the leaf are also reflecting near-infrared light we cannot see. This reflected near-infrared radiation can be sensed by satellites, allowing scientists to study vegetation from space. Using these data, scientists can identify some types of trees, can examine the health of forests, and can even monitor the health of vegetation, such as forests infested with pine beetles or crops affected by drought. Studying the emission and reflection of infrared waves helps us to understand the Earth system and its energy budget. Near-infrared data can also help scientists study land cover such as changes in snow, ice, forests, urbanization, and agriculture. Scientists are beginning to unlock the mysteries of cooler objects across the universe such as planets, cool stars, nebulae, and much more using infrared waves. Microwaves can pop your popcorn. They can catch you speeding. They carry thousands of phone channels to speed your calls. But can microwaves help us learn about our world and our universe? Let's find out. With wavelengths ranging from 30 centimeters down to 1 millimeter, microwaves fall between radio waves and infrared. Microwaves are used in Doppler radar, which is widely used for short-term localized weather forecasting and what you see on TV weather news. Satellites have revolutionized weather forecasting by providing a global view of weather patterns and surface temperatures. This unique perspective has greatly increased the accuracy of tropical storm and climate forecasts. Different wavelengths of microwaves, grouped into bands, provide different information to scientists. Medium-length, C-band microwaves penetrate through clouds, dust, smoke, snow, and rain to reveal the Earth's surface. Satellite microwave measurements reveal the full Arctic sea ice cover every day, even where clouds exist. These measurements show great variability from year to year, but also an overall decrease in Arctic sea ice since the late 1970s, illustrated here with maps and a time series of Arctic sea ice in September at the end of the summer melt. The Japanese Earth Resources satellite uses longer wavelength L-band microwaves for forest mapping by measuring surface soil moisture, such as this image of the Amazon basin, to identify areas of recent deforestation. L-band microwaves are also used by global positioning systems, such as the one in your car. Scientists routinely combine microwave information with information from other parts of the EM spectrum to study the composition of cosmic dust, or of a supernova, such as this supernova image that combines X-ray, radio, and microwave data. This recently known supernova in the Milky Way exploded just over 140 years ago at the time of the American Civil War. One important phenomenon is unique to microwaves. In 1965, using long L-band microwaves, Arno Penzias and Robert Wilson made an incredible accidental discovery. They detected what they thought was noise from their instrument, but was actually a constant background signal coming from everywhere in space. This radiation is called cosmic microwave background, and if our eyes could see microwaves, the entire sky would glow with a nearly uniform brightness in every direction. The existence of this background radiation has served as important evidence supporting the Big Bang theory for how our universe began. Microwaves have become both staples and wonders of modern life. They are also the backbone of communications and of Earth's sensing systems, and they are an excellent guide to the ancient history and origins of our universe. Swirling spiral arms of galaxy M33 can be seen in visible light, but the true extent of these spiral arms are revealed in ultraviolet light. Just as a dog can hear a whistle just outside the range of human hearing, bugs can see light just outside the range our eyes can see. A bug zapper emits this ultraviolet light to attract insects. Johann Ritter conducted an experiment in 1801 to find out what, if any, electromagnetic waves are beyond violet. Ritter knew that photographic paper would turn black more rapidly in blue light than in red light. So he tried exposing the paper beyond the violet end of the visible spectrum. Sure enough, the paper turned black, proving the existence of light beyond violet, ultraviolet rays. These ultraviolet rays, or UV radiation, vary in wavelength from 400 nanometers to 10 nanometers and can be subdivided into three regions: UVA, UVB, and UVC. Visible light from the sun passes through the atmosphere and reaches the Earth's surface. UVA, long-wave ultraviolet, is the closest to visible light. Most UVA also reaches the surface, but shorter wavelengths, called UVB, are the harmful rays that cause sunburn. Fortunately, about 95% of these harmful UVB rays are absorbed by ozone in the Earth's atmosphere. UVC rays are the shortest and most harmful and are almost completely absorbed by our atmosphere. The ozone monitoring instrument aboard NASA's Aura satellite detects ultraviolet radiation to help scientists study and monitor the chemistry of our atmosphere, including UV-absorbing ozone. While atmospheric protection from harmful UV radiation is good for humans, it complicates the study of naturally produced UV rays in the universe by scientists here on the Earth's surface. Young hot stars shine most of their light beyond the visible light spectrum at ultraviolet wavelengths. Scientists need telescopes in orbit above the Earth's UV-absorbing atmosphere to find and study these UV-bright regions of star formations in distant galaxies. New young stars in the spiral arms of galaxy M81 can be seen in this Galaxy Evolution Explorer GALEX image from NASA. Chemical substances, both atoms and molecules, interact with UV light, making this region particularly interesting to scientists. An ultraviolet instrument aboard Cassini has detected hydrogen, oxygen, water ice, and methane in the Saturn system. UV data have also revealed details of Saturn's aurorae. Scientists also use UV waves shining from distant stars to view permanently shadowed regions of lunar craters. The Lyman Alpha Mapping Project, or LAMP, instrument aboard NASA's Lunar Reconnaissance Orbiter can use this faint starshine to look for possible water ice on the moon. Ultraviolet rays may be harmful to humans, but they are essential to studying the health of our planet's protective atmosphere and give us valuable clues to the formation and composition of distant celestial objects. Created by the hottest, most violent, and most energetic objects and events in the universe, gamma rays travel across vast stretches of space, only to be absorbed by Earth's atmosphere. Scientists had no way to detect and study gamma rays from the cosmos until high-altitude balloons and rockets carried gamma ray sensors above the atmosphere. Deadly to humans, gamma rays are created on Earth by natural radioactive decay, by nuclear explosions, and even by the lightning in thunderstorms. Coronal mass ejections from our sun emit gamma rays, followed by masses of charged particles. Monitoring these gamma rays provides scientists with an early warning of incoming charged particles that may cause disruptions in power and communication networks. The most energetic of all EM waves, gamma rays carry enough energy to kill living cells. Doctors are able to selectively use gamma radiation to destroy cancer growths. Gamma ray wavelengths are the shortest of all electromagnetic waves, about the size of an atom's nucleus. In fact, it is so short that the rays sail through atoms as easily as comets sail through our solar system. This makes detecting gamma rays difficult for scientists. Gamma ray detectors typically contain densely packed crystal blocks. As gamma rays pass through, they collide with electrons in the crystal. The sensor doesn't directly detect gamma rays. Rather, it detects the charged particles created by those collisions. Scientists have used gamma rays to determine the elements that make up Martian surface soils. When struck by cosmic rays, chemical elements in soils and rocks emit uniquely identifiable signatures of energy in the form of gamma rays. The gamma ray spectrometer on NASA's Mars Odyssey orbiter detects and maps these signatures, such as this map of hydrogen concentrations. Gamma rays stream from stars, supernovas, black holes, and pulsars to wash our sky with gamma ray light. NASA's Fermi Gamma Ray Space Telescope imaged the location of these sources, mapping out the Milky Way galaxy by creating a full 360-degree view of the galaxy from our perspective here on Earth. While the visible light sky is predictable and follows regular patterns, the gamma ray sky does not. Bursts of high-energy gamma radiation arrive from deep space every day. These explosions of gamma rays last fractions of a second to minutes, popping like cosmic flashbulbs, momentarily dominating the gamma ray sky and then fading. This video of the Vela pulsar beams gamma rays every 89 seconds as it rotates. Gamma ray bursts are the most energetic and luminous electromagnetic events since the Big Bang and can release more energy in 10 seconds than our sun will emit in its entire 10 billion year expected lifetime. NASA's SWIFT satellite recorded this gamma ray burst of an exploding star 13 billion light years away. It is among the most distant objects ever detected when the universe was just 630 million years old. A recent observation of a gamma ray burst produced the greatest total energy to date, equivalent to 9,000 typical supernovae. By continuing to study gamma rays, we will unlock important new understanding in astronomy, its use in medical treatments, and allow us to further enhance our protection for our satellites and other electronics here on Earth. A star explodes in a blinding supernova, spraying X-rays across the galaxy to tell its tale. X-rays also tell a dentist which tooth to drill and a surgeon which bones to mend. In 1895, Wilhelm Röntgen discovered that firing streams of X-rays through arms and hands created eerie but detailed images of the bones inside. X-rays are high-energy light rays with wavelengths between 3 and 0.03 nanometers, so small that some X-rays are no bigger than many individual atoms. In laboratories, scientists fire beams of X-rays at unknown substances to learn what elements they contain and to decode their atomic structure. This is how scientists unraveled complex molecules like penicillin and DNA. Scientists can also detect the X-rays emitted from extremely hot and energetic objects in the universe. NASA's robotic rovers recorded X-rays to identify the spectral signatures of elements, such as zinc and nickel, in Martian rocks. X-rays can also reveal an object's temperature, since temperature determines the wavelength of its radiation. The hotter the object, the shorter that wavelength is. X-rays come from objects that seethe at millions of degrees, such as pulsars, black holes, supernovas, or the plasma in our sun's corona. Our sun has a surface temperature of around 6,000 degrees Celsius and radiates most of its energy in visible wavelengths. But it is easier to study the massive energy flows in the corona's energetic plasma by observing X-rays, like this image from the Hinode satellite, a joint Japanese-NASA mission. NASA's SOHO satellite produced these X-ray images of the sun that allow scientists to see and record these energy flows within the corona. NASA's orbiting Chandra X-ray Observatory detects X-rays created by objects spread far across space, such as this supernova explosion that occurred 10,000 light-years from Earth. The colors in the gas and dust cloud correspond to different energy levels of the X-rays created by the blast. X-rays at different wavelengths provide information about an object's composition, temperature, density, or its magnetic field. Human eyes may not be able to see X-rays, but from seething cosmic bodies to individual atomic elements, X-rays provide a wealth of information to exploring scientists.
Thanks for being patient through that. I know it was a long video. I really like it though, because I've said this a few times before. I find it very humbling myself to realize that, like, man, we are only sometimes just discovering how some of this stuff is useful. 10 years ago, we did use microwaves for cell phones the same way, right? And so, like, the way that they're currently trying to figure out how to use all this different electromagnetic spectrum stuff. I mean, obviously, most of this was tailored towards like expanding universe, cosmos stuff. But I mean, I thought it was also useful because it kind of showed you where these waves are applicable on Earth as well. Here's what I need you guys to know. I need you to know which order they go in, at the very least. Okay. And if we can, maybe knowing a little bit of their frequency and wavelength. So, which are the longest waves, if you can do it without looking? Radio. Yeah, radio waves. Followed by, good, which seems weird because micro you'd think would be small, but it's just smaller than radio, that's all. Next, good, infrared. Followed by visible light. So from red all the way down to violet. After violet, they're going to get ultraviolet. Good. Ultraviolet leads into X-rays, and then into gamma rays. They didn't really mention cosmic rays either, but to be honest, I mean, we know very little about cosmic anyways. I mean, again, I only really know what I research, and even then, if what I research is a fraction of what people know, it doesn't seem like there's a lot we know about cosmic rays. So, does that work? Okay, I've got a few last slides and then we'll call it a day. Sorry it's such a long lesson to start off with. Last thing I want to mention is just the idea of how the science has changed over time. You guys have heard of the scientific method at some point before, I'm guessing, right? The idea of just like how scientists, I don't know, collect data. I pulled this chart off the internet. You observe something, you make a general idea, hypothesis, you do an experiment, maybe you have to redo the experiment. I don't actually tell what this one was right here. You know, eventually you make a conclusion, and hopefully a conclusion leads to a theory. What I want to just talk to you guys really briefly about is two different models of light and EMR that were developed hundreds of years ago that we're really still working on figuring out what really is happening. The two main models are that light is a particle or that light is a wave. You guys ever heard of this before? If you watch Big Bang Theory, actually Sheldon talks about it a few different times. The idea that light can act as either a particle or a wave. We're going to spend a whole topic on this more in topic 7, wave-particle duality, but I just need to mention it beforehand because it'll come up. I like this diagram here. Light is a, hopefully you can see this, it either says particle, P-A-R-T-I-C-L-E. You guys see that? Or if you look at a different perspective, it's a W-A-V-E. There's this big theory in science that light acts as both a particle and a wave. So let me just talk about that real briefly. Back since the time of Isaac Newton, people thought that light was actually a particle. And they had some reasons for it. Here's some evidence as to why they thought that light was more or less like a thing of matter almost. Okay. They knew that light traveled in straight lines, and the reason why they knew it traveled in straight lines is because of shadows. Right? When light hits an object, it can't pass through that object, and so therefore there's a shadow left where the light hits the object, but not around the edges of it. Does that make sense? So they knew it traveled in straight lines. They knew it could be reflected. They knew it could travel through a vacuum. How else could it do so and get from Earth unless there was something for it to travel through? So Newton thought light was a particle. Newton was such an influential guy in science that really, as long as he was alive, no one dared to argue with him. It's kind of weird to think of, but all other scientists kind of I wouldn't say bowed down to him, but if they had their own ideas, they kind of kept them to themselves until Newton died, because they just didn't want to argue with the great Isaac Newton, I guess. So afterwards, scientists tried to suggest, well, maybe light isn't actually a particle. Maybe light is a wave, which is what we were just talking a lot about. So here's some evidence for light being a wave. Grimaldi showed that light would diffract when passing through openings.
Bobby Curran, can you please go to room 115? Bobby Curran, please go to room 115.
When he looked really closely at shadows, he actually discovered they weren't perfectly sharp. They were actually kind of fuzzy along the edges, which maybe shows that light actually has the ability to move a little bit around. Okay. I don't actually know how to pronounce his name. Poisson. I don't know. Okay. I think he's French. He thought that light should not be able to diffract around a disk, but a guy later actually discovered this and named it after the first guy as a joke. And let me see whether this diagram helps make sense. Okay. What this first guy thought was that this should not be possible. If you have a light source right here in an object, you would think that you should have a shadow up to here and up to here, right? You're going to get a big circular shadow. What we've discovered actually is that light has the ability to actually bend backwards around this object, and you'd actually get a bright spot right in the middle. I don't even fully understand it, to be honest, but it happens. And so this guy right here thought it should not happen, and then this guy right here discovered that it did happen, and so he named this spot right here after the first guy as a joke. Oh, that's kind of cool. So the idea basically is that light can actually bend around objects. So the light travels this way and actually then bends around the corner, which then proves that, well, particles don't do that. Maybe waves can bend, though. Another guy here, Huygens, I don't know how you say his name, not that it's relevant. He also discovered that waves have this ability to refract. I mentioned this term earlier, the idea of refracting. If you have a wave that goes into water, some of it might get reflected back out, but it might not go straight through on a straight line. It might actually bend, and that would be more of a property that might indicate a wave rather than an actual particle. Make sense? We're going to talk about this experiment a lot more in topic 7. This idea, it's called the double slit experiment. Guy basically sends light through a just a small opening. And as it goes through the small opening, if it's a wave, it kind of goes out in concentric circles, kind of like how you drop a rock in water and it makes waves through it. right? So if light actually acts like a wave, here's what they discovered is this light would go through here, it would radiate out in fronts going forward, and then if it goes through two different slits, you'd get a whole bunch of interference patterns, and you actually get like light, dark, light, dark, light, dark. Make sense? If light was a particle, what would the screen look like? Black. Because what would happen is this light particle would go right through here, it would hit this screen right here, and nothing would happen. Does that make sense? And yet somehow this light goes through here and then manages to like radiate outwards and actually creates appearance on a screen. So, okay, long story short, here's a few terms I want you guys to know, mostly because we need them over the next couple of like lessons. We actually use the term quanta, which is like similar to like quantum. We're kind of getting into some of this really fancy new age physics, like quantum theory, if you've heard it before. Planck decided that maybe as a model, light actually acts in like packets of energy. And maybe you've heard this term before. Einstein called them photons. The video there mentioned that. The idea that maybe light is actually both a particle and a wave. And as a particle, it kind of gets shot almost in like discrete, like almost like a ball, basically, right? And this is a photon, and that's a photon, and that's a photon. And it shoots them in like, I imagine like a paintball gun, kind of, where it keeps shooting them rapid succession as like an actual object. But yet, light is not actually an object either. It also has electromagnetic properties. So it's really, this sort of stuff is still being figured out and looked at. And scientists are still discovering this. To be honest, it wouldn't surprise me 200 years from now in schools that we teach something completely different because we actually understand it better.
Like one of those things where it's like they wish they could go back and change it. 'Cause
We might have that problem in 200 years, yeah. Which is one of the things that I love most about chemistry and physics, is the idea that, you know, for years scientists thought the Earth was flat. They taught that in schools, you know. They had proof for it, but they were totally wrong. You know? And this is the same sort of thing, only this is our modern stuff. So the stuff that I'm going to teach you for more or less...
Comm students, please go to room 211 for comm today.
The stuff that I'm going to be teaching you guys for pretty much the rest of the course is theories and ideas about light and quantum stuff that these theories are still being worked on, still being developed. They're not firm, if that makes sense. Like, scientists are still working on this to this day. So you guys are kind of getting in on the ground floor of developing theories. So I have to be honest, I'm not an expert in this, but no one really is. I mean, maybe people who have their PhDs at universities are, but, you know, so anyways, I found that really cool. Also kind of scary too, though, to be like, how do I teach this when this has not even been fully discovered necessarily? So. Okay, questions? All right. Thanks for bearing with me for a long lesson. It's a lot of information up front. So that's all I got.